by saying thank you to everyone. Thanks for having me here. Thank you, Carlo, for inviting me. And thanks for giving me some Dutch cheese, which I'll say I've missed a bit. Although I've got to be quiet, my Swiss friends and colleagues get really angry if I say that. So yeah, as Carlo said, I worked with him and a few others on this particular topic. So let's start. So the first question is, why are we even interested in doing this? So in Zurich, similar to the Netherlands, of course, there are common intersections, but also there are complex signal programs. So this intersection here is one of the busiest in Zurich, not only for private motor vehicles, but also for trams. So a lot of conflicting movements. We've got really complicated signal programs with, as I said, public transport priority. And there's also a large number of signals in general. So if you want to simulate, for example, a city, well, this is just a section of the area outside of Zurich. You can see there are a lot of traffic lights. And you can imagine each of those have these complicated programs with public transport priority. And the other thing, which is perhaps a bit unusual, is that we've tried asking the companies which install these traffic lights, can you tell us, give us a simple instruction of how your traffic lights work so we can simulate. And it's surprisingly complicated because different companies have different techniques. Once they are programmed, the cities don't necessarily know themselves how they were programmed, it just works. So this it pushes us towards trying to develop a method where using observations from the intersection, which are more readily available, from the detector loops, which are present, for example, can we sort of reverse engineer these signal programs at a large scale? Because there are so many, we don't want to be manually figuring out everything. And this is really important to create accurate digital twins. When we talk about digital twins, we're talking about essentially a digital simulation of the city and the traffic in the city. There's a lot of time that's spent talking about accurate demand, accurate networks, but there's not been as much focus on accurate traffic signals. And in cities where the traffic signals are close to each other, they impact each other. So it becomes very important to get an accurate representation of what the signals are doing. So how are we going to do this? The first thing we're going to do is start with our data. So here you've got in blue some detector signals, and at the bottom the state of traffic signals. And we're going to combine that with knowledge of which signals are which on this map, for example, which detector is which. And we're going to try and learn how to predict the next stage, essentially. How do we predict what the traffic signal will become in the next second, in the next 10 seconds? We're going to do that using decision trees. Talk a bit more about that later. And the idea is that once we have decision trees, we can then feed the live data from the intersection as we have it, and then predict the next stage in the simulation. So you see in the simulation, we've got detectors that are placed, just like in the real one, which you see here. And we can essentially run a program which is live, seeing the value of those detectors, and trying to reproduce the behavior which we've seen in the real data.
So here, an assumption, those blue rays time series, those are loop detectors. So checking if there's a car on that specific point.
So in the next couple of slides, we're going to formalize it a bit. But the idea is it could be any kind of detector. So it could be a loop detector, it could also be a camera, for example.
Yeah, but it's basically the information that you extract from there is whether there's car or not. Therefore, an implicit assumption is that the state of the traffic lights is not only time triggered, but also depending on events like having car flow.
Yeah, absolutely. So how are we going to tackle this problem? So we're going to start by formulating the problem. So what is a traffic signal program, for example? We're going to take a look at some examples which we've created using SUMO, which is a microscopic traffic simulator. We're going to see some results, also including real data. And then hopefully we're going to be able to make a nice looking simulation where the traffic light is going to behave in a similar way to reality, to what we'd expect. So let's start with the problem formulation. So one of the challenging aspects of this particular part, where we need to essentially think of what is the general traffic controller. So first thing we're going to do is find a way to represent the state of a signal at a given time. So if you want on this, there's 4 different signal states here. So you can see a pretty classic intersection. And essentially, we're going to write it with these S's. So we're going to say that at a given time, K, we have a certain, so one of these small S's here represents a single arrow, if you want, on this graph. And then the vector is going to represent the entire intersection at that point in time. Then we're going to also represent the states of the detectors. So for the moment, we're going to assume it's a detector which is either 0 or 1. So for example, measuring the presence of a vehicle. In a similar way, we're going to have a very general definition where we consider the entire history of every detector to start, and the entire history of every single state. Then we're going to represent the program as an automaton. And the function that we're going to be really interested in is this delta. And the delta says that for a given single state and history of states, and a given detector state and history of detector states, what is the next state? And that's going to be important. So this topology here is just a random example. But you could imagine that you have different states that are being visited. But we want to know, how do we go between them? How do we decide which state is coming up next? That's what we're going to be focusing on. So we write the automaton in this more formal way. I can explain a bit more of this later. But one of the problems we have here is that we have this very general definition, which is, for example, taking into account the entire history of the detectors forever, right? And it's unreasonable to assume that to determine the next state of the traffic signal, we are looking at what the detector state was a week ago, for example. So we're going to do what I call input truncation, which is essentially just simplifying that. So trying to get out of that the most important data to feed to the decision trees ultimately to predict the next signal state. So for example, instead of storing the entire history of all the signal states which have occurred, we can store the last C visited signal states. So I don't mean over the last 5 seconds, but I mean the 5 separate states which have occurred in the past. And we're also going to record, for example, the time since the last change. And again, a bit of an unusual notation perhaps, but I'm going to write this S hat here, which is the truncated representation. So the idea is that we can get to this from the entire representation of the whole history of the states. So it's a more compacted version of the data. For detectors, we're going to do something a bit similar. Instead of storing the value at, for example, any millisecond, is there a vehicle right now or not? We're going to say, how many seconds has it been since there's been a detection? So again, the idea really is to try and create a more simplified version of this very large data which we have. And now we're going to try and find this slightly different delta, which goes from these simplified states and still predict what the next traffic signal state is. And a little note on why I've been talking about decision trees. This is also an assumption we make. So it feels reasonable that a traffic light controller is going to make if-then decisions, for example. If there is a queue here, then we maybe want to do something a bit different. Also, in other research we've seen, random forests and decision trees tend to be better at identifying traffic light behavior compared to neural networks, for example. And that is because of the inherent rule-based structure of a traffic signal controller. So just a quick note on how we're going to decide whether we've been successful in our task of predicting the next signal state. So the first thing we can think is, how good were we at guessing what the next state was? So this is sort of the naive approach. We can say, okay, 90% of the time we've guessed the correct next state based on the truncated representation, as I said. But there are some problems with that, so I'll talk about those in a second as well. So we're also going to look at transition accuracy, which says, given a transition has occurred at a certain time, what percentage of the transitions were correctly identified? When I'm saying transition, I mean changing from one state to another. If we just think about the next phase, it would count as a success to have predicted the next state is the same as the current one, for example. But again, I will show why this leads to some issues later. So let's talk a bit about some, we've put this into, applied this in a couple of ways. So let's see how that looks. So one of the interesting approaches that we took in this work is, because we are trying to study something which we we don't know, we're trying to reverse engineer a traffic signal program. We can get data for a real intersection, but we don't know what the real traffic signal program is doing. So one of the approaches which we took was to first create an intersection in the traffic simulator, so in SUMO. So again, it's a four-way intersection. We put some detectors on it. And we're going to program ourselves this traffic signal in the simulator. So to start with, we're going to have a static program. So one which doesn't depend on the presence of vehicles or not. And so we're going to just define these states. These are the same ones we saw earlier. And then we're going to create this delta function, which is the one that we're going to try and find later. Essentially, what this says is that we're going to be 3 seconds when there's amber, and then we stay 30 seconds in each of the green phases, and it will essentially just loop. So we start with a more simple program, one which doesn't depend on the vehicles triggering the detectors. And what we see, okay, is that after giving it 102 seconds of observation of this intersection, using decision trees, we're able to reproduce 100% of the time the correct signal program. So what that means is that in the decision trees, they have determined that the output of the detectors is not important, and it's just basically the time, number of seconds since the last detection, combined with what the last state is. Right, so this is the automata again. And then when we look at the decision trees, we can read from there and identify these parameters from the traffic light program we put in ourselves. So we didn't tell the decision trees that this is what happened. They observed the data, they observed what was happening when the traffic was running over the intersection, and they determined that this is a perfectly deterministic way of essentially matching this program. So that's not so interesting because, of course, in Zurich, in the Netherlands, we have actuator programs where vehicles will affect the determination of the next phase. So we're going to stick with the same 4 phases, but we're going to have a bit of a more complicated program. The idea is we're going to imagine that this is a really busy east to west main road. So we're going to try and favor the signal state number 4 over there. And we're only going to let vehicles come in on the side when there is a gap, for example. So this is essentially the idea of what the program that we're going to create is. And if you write it down, it starts looking a bit more complicated. And I'll just do one more. All of this logic is going in there. This is just to tell it to not interrupt the main road until there's a gap. So you can see, for example, the gap is this not main flow, and everything else is just going to make sure that it only switches to the side road when there's demand, for example. The point is, this is already much more complicated of a program, right? So the decision trees would have to figure out all of this stuff from the data. And the question is, can they do it? So the first approach which we had is, again, let's start by making it easier for decision trees. And let's pre-compute all of these variables and give them to the decision trees. So we give them the value 0 or 1 for each of these variables. And we're going to see whether or not it's able to figure out that. Then we get rid of them. And the question is it still going to be able to figure out all of this complicated logic which is hidden under? So let's look. The first results is where we give it the values, these pre-computed values. I call them artificial features. And again, you can see that it doesn't take a lot of duration here. And again, when I say training duration, I'm perhaps using the wrong term. I mean that I've given it 100 or 300 seconds of observation of the jump. So it's able to figure out pretty quickly how that works. But we've given it a lot of information. We've told it this complicated logic. And if you remember, one of the things we want is to not have to look at individual junctions and determine this kind of stuff. What you see is when you look at the tree, it's very quickly determined that the switch to secondary is very important. Well, of course, because that's the way we define logic. Now, you remember earlier I said that the next phase accuracy is not a great metric. And this is the reason why. Because the first thing the decision trees will learn is that, well, 75% of the time, the state is green on the main road. So let's just always predict that. And you see that it shows good there, but then when you start taking the transitions into account, that corrects for that error. So that's why we have this second performance method. Now, what's really interesting is when we remove. these artificial features, right? So we remove all of them. And what we see is that it now needs, quite a bit more time, but crucially, it's still able to figure this out. And when we look at decision trees, they start getting really big, okay? Because this is essentially capturing all that logic which we wrote into the program which we gave to the simulator. Now, we've looked at the simulator. So what we've done so far is that we've programmed the traffic light in the simulator, we've ran some traffic on it, measured the traffic, and then given it to decision trees and see if it could figure out the traffic light program. So now we're ready to look at the real intersection, give the real observation data of the intersection in Zurich, and see what the trees can figure out. So we're going to look at this intersection here. For reference, ETH is to the right, and that's the main station. So very central in Zurich. We've got a location where there is public transport, which has priority, which is also merging with a lot of private transport and pedestrians. And again, that's this particular intersection. And when we look at the results, we see that it still works reasonably well. So it's not 100% accurate in the prediction. And I will talk a bit about that in a second. But again, what's interesting with this result here is that we haven't had to tell it how the intersection is operating. We've just given it the data, and it's figured out from there what is the most important variable to predict the next phase, for example. Let's look at some simulations, because that's always fun. So we start again with the first scenario where we had the really busy east to west main road, and we don't want to block the flow. So when there's a gap, then we can let people in the middle go if they're waiting. Otherwise, we don't block the main flow. And what you're seeing here is not the simulation running with the program which we programmed. This is actually the decision trees deciding what's the next phase based on having learned the program. So I can play this. All right, and so what you'll see when we give a bit of time for the vehicles to appear is that we have this behavior which we had programmed in. So a busy main road, and you can see that it's not going green onto the side until there's a big enough gap. There we are. So again, it's just important to understand that in this particular simulation, I didn't program the traffic light. It has just learned it from the data, which we got from another scenario where we programmed it. But the whole point is that it was able to figure out all of this just automatically. But this is even more fun. Let's look at the intersection in Zurich. So you'll see that every so often the tram will appear, and so when the tram comes, we hope that it doesn't have to stop for too long. Let's see. That seems like they didn't have to stop that much. Now, again, it's very difficult to give a score on how accurate this simulation is, because we don't know what the real controller is doing. That is the fundamental problem. But it looks quite close, and then we've also, I don't think there's time in this presentation to talk about it. We've taken a look, we've done some statistical analysis on the observation in the with the real data, and we've compared it to what's come out of this simulation, and it matches much more closely than if you use a static program, for example, or try another. As a little extra, I have triggered the detector up there manually. So I've told the decision trees that there's a tram waiting there, and what you see here is that it's going to keep trying to get the tram to pass, right? Even though there is none, right? Because here I've overridden the detector. But what you see here is that the behavior of the traffic light is changing in response to traffic. In this case, the tram traffic. And again, I've not told the program, I've not told the decision trees that the tram should have priority. It's just something which it's learned from having the real data. So you can see how that green light for the tram is green almost all the time. And eventually it reaches a maximum. I don't know what the maximum is. It just figured it's something out. And then it lets a couple of people and then tries to put the tram green. And so if a detector breaks in Zurich or if a tram gets stuck, this actually happens. I've seen it. It just stays green even though there is no one. So this is also kind of matching what we expect. Let's go to the next slide. Now, along the way, I've created some visualization tools. I can go over this a bit more quickly. So this timeline here is to essentially try and observe what's going on at the level of the traffic lights in a timeline view. At the top, you can see that's what the real data looks like. And at the bottom, at A is with our method. So one thing you see is that the distribution is a bit more even of the vehicles that appear in the simulation. That's just because of the way SUMO is. But crucially, you see, if you just use a static traffic light, it looks nothing like the observation data, whereas our method, it matches much more closely. Again, there's a bit more rigorous comparison. I can just say, oh, it looks close enough, but we actually did do a bit of analysis. And then this is sort of representing that automata. You can see that there are a lot of connections, and that's because there's still a lot of work to do in this. So this worked quite well, but there is something to say that maybe we should be looking at learning the transitions rather than learning the states, because sometimes the controllers, they are working towards a transition rather than considering each state dependent. But here you can see there are a lot more states this is in the Zurich Institute. And then a quick note about the size of decision trees. So they're quite big, right? So we saw for the actuator program, they were getting really big. For Zurich, it's even worse. And one of the things you can say is, well, how about we just prune the tree? And the problem is that it's not something which we can do easily, because one of the important things about the traffic signals in Zurich, for example, is that they prioritize public transport. And to be able to do that, the decision trees have to learn that when a tram comes, which isn't that often, it's really important to give the tram a green light. If you say, oh, we can prune the things which don't happen that often, then it will just forget about trams. So we can't do that so easily. So to conclude, we've created a tool which allows us to reproduce in simulation unknown traffic light controllers based on observation data. We've done this with the decision trees. When we have a known signal program, which crucially makes its decisions based on the same parameters which we are taking into account, so the number of seconds since the detector detected the vehicle, we get perfect replication of the program. When we don't know the program and it uses parameters which we don't know, we get a pretty good estimation. And again, because we're using decision trees and we're doing this in Python, it's super easy to then control the signal in SUMO. In terms of future work, so we want to look at multiple signals next to each other. We know that they're coordinated, and that's a lot of extra work. We have to start worrying about the size of the state getting really big. And also, we'd like to find a way to reduce the size of the trees without losing that public transport priority. So thank you very much for listening. I will quickly talk about something that we're working on now with Carlo, and maybe we can do questions after so that we can just finish talking first. So in all this work with SUMO, we've run into a lot of pain, right? So there's a lot of things which we've had to do again and again. I will give some concrete examples, but what we're working on now is a tool to essentially make this much easier. So what we want to do is make it easier for control people to work with the traffic signal. So I'll give you a concrete example from the work that I did. Let's say, for example, we are looking at the Zurich intersection, and we need to make sure that it works on multiple different right. So the traffic levels are random, for example. We want to average out, say, 100 simulations. And the way that you need to do that in SUMO, it's not you just say 100 and then it will average everything. You have to run the simulation multiple times, copy stuff to a spreadsheet, do averages. So one of the things we want to do is essentially create a UI, a tool, where you can just say, I want this simulation 100 times, and then you can just get the average. I think Carlo will be happy to share a bit more about this project. I've got a little video showing you a demo of what we're doing. Let's see. All right, so what I'm going to do in this video is we're going to create a scenario, for example. So it could be a service station, which I think is the one that I'm going to create here. So here's the scenario. It's essentially a long motorway. We're going to have a ramp. So we're going to do some ramp meter. That's the idea. So we add some experiments, which the idea is this could be using different types of controllers, for example, to evaluate how, in this case, using a ramp meter versus not using one. And then we can create a new run request here, and we can immediately say how many times we want this run to happen so that we can average everything. So we'll just do 2, because originally this video was live and I had to wait for them to run. So you see that it runs for you, the 2 separate runs. displays. I think you see that those there. And then we skip a bit, they're now done. And visualizing all these statistics is directly built into this tool. So you've got these subscriptions which represent essentially samples of what's going on in the simulation. For example, the interval occupancy of a detector. You can open it, and you can see this is the average over the actually, no, this is just one of the running. Sorry. So remember, we've run this simulation twice, so we can put both of them together, for example. That, and then we can also average it. And then you can directly download the data from here. So here we've only got 2 runs, so it's pretty manageable to still do it manually, but you can imagine as you put more and more runs, it can start getting more and more painful to do this. And again, I think in general, we think that's quite a high, there's a barrier to entry, right? To use this traffic simulator to do control research, because you're going to start having to essentially create some sort of infrastructure yourself. I was using a script to run the simulation, change this number by 1, run it again. And we really want something which is just a bit nicer to use, a bit easier. And for this, we also need your help. If you're doing any research involving traffic simulator and SUMO, please tell us the things that drive you crazy, because this is exactly the kind of things we'd like to put in this tool to make it easier. And this is what I'm doing for the moment in Zurich with Carl. What's going on here is that we've created another experiment. This is without a ramp meter. And we want to compare them on the same graph to try and evaluate the performance of this ramp meter, for example. And that's something we can do. So we can add the other run request to compare. We select that one. And then we'll also select the average of both of those executions. And then we'll be able to directly compare them on the graph. So here you can see that with the ramp meter, the flow is much more even. Again, the particular variable here is the occupancy of a detector upstream on the highway. So you can see that without the ramp meter, it's higher occupancy, which means it's more stop and start traffic. So this is just a little scenario to show you what this does. Another part that's important is that we have quite high focus on persistence. So you can go back in time and say, see the scenario which generated this data. And this is all in a database, so you can always go back and you can really compare exactly what was the difference between the 2 scenarios which created this data. Here you see just the controller has commented out. That's how we did it without the ramp. Yeah. So that's what we're working on now. And yes, we need your help. Always happy to hear what drives you crazy with SUMO, because that's what we're working on. And I think the presentation's gone. I think that's it. Right here. All right, so thank you very much. That's all the slides I've prepared. Thank you very much. And yes, please, if you have any questions.
I have many.
Absolutely.
One is a bit of a clarification. You can go to the copies finance definition with the R, G, or United States.
That's good. Right.
So I was a bit confused about exactly what are. Sorry, I think you had. All right. So I'm looking at that intersection.
Yes.
And I see there are actually. I'm interpreting the plotting up as if there are 9 different lights.
Yes.
Each of them with 3 different states.
Yeah.
So that's 3 to the power of 9
Absolutely.
possible configurations.
Yes.
But you're also taking into account history, right?
So what you
the
think?
state,
Yes.
basically those strings that you're writing there will be 3 to the power of 9 multiple times. Those are the states.
It gets very big. So in this situation here, the signal to go straight and turn right is combined.
Right? Okay, but just conceptually,
yeah.
Your states are that. These combinations of, are representing, let's say, the past 3 states of all the lights that you think that are interconnected with each other.
So are you talking about the truncated one or the full?
The truncated.
Yeah, exactly.
The full one will be the full history.
Exactly,
right? So
absolutely. Exactly, yeah. So they're just strings that look like this, basically, right?
Yeah,
That's
the thing is that to me, I was kind of puzzled because there you have only 4 states.
Yes.
While from the plot on top, I would presume that you have here, I don't even know, thousands, if not more than thousands possible.
So in this
states.
Yeah, so the way we do this in practice is that we look at all the states which have happened in the training data, and those are the states of the automata. And then we are deciding how to go between those, right?
Okay.
And the truncated data, what we do with this particular state stuff is we just think, what are the last, I think in practice I use the last 2 states that were visited, right? So in this example with this automaton, it will always be that the previous state visited was the one before.
Yeah.
Right. But when you use a controller, which is, when we don't know what the traffic signal does, then it's going to be more important.
So now that that's more or less clarified for me, I was wondering, in a normal, these traffic lights of a junction usually or often do not depend only on the traffic lights of that junction, but on what happens upstream,
Exactly. Absolutely.
downstream, on the sides, whatnot.
At least you've got a green wave, for example.
But then that example, so in that situation, because we're talking about pruning, right? So a very natural way of pruning, that you may not have access to the logic, but you certainly, because it's probably much easier to get access to the interconnection of which traffic lights are getting information from which other traffic lights for the decision. And that will allow you to at least reduce the size of the states that you keep in consideration.
I think so. It's not always easy to know which signals are interconnected. Okay. So I can give you a quick example. So there are some times when it's pretty clear, right? If you have a green wave corridor, which you know, right, then you know they're interconnected. But in Zurich, did you know, for example, that there are traffic detectors that are in the center of the city, and that if the center of the city starts getting congested, every traffic signal at the entrance is going to have much less green time. So you need to know that there is a dependence on detectors that are all the way over there, for example.
And that is also not easy access.
That one is no, because it's research. But the point is, it's possible.
Yeah.
Right? It's possible. And sometimes 2 intersections might be close to each other, but if there's very low traffic flow between that link, they don't need to be interconnected. Right? You only need to interconnect them if essentially the accumulation space in that link is not enough for the capacity of the wider network in that area.
One other clarification, sorry. I was curious because a natural question now is also what time step to take for this sample, right?
Yeah.
And I was wondering why. I mean, I understand this is kind of a straightforward way.
Yeah.
This is time and then
Yes.
But essentially, what you're doing is just identifying automata traces, right? In a nutshell.
Mm-hmm.
And I was wondering, did you guys think about identifying time automata traces?
So I didn't have the time to look into much complicated than what I've shown.
Okay.
But
you know what I'm referring to?
I don't know.
Do you know what a time automata is?
No.
Okay, so basically in a nutshell is that you will have a continuous variable for the plot.
Okay.
And your transitions depend not only on the keys of your place, but also on the values of a clock or multiple clocks. That way you can essentially get rid of having to look at the history.
Yes.
You won't just directly be looking, because you also incorporate at some point you decided to compress these signals as the time between.
The time since the
changes, right?
Yeah.
I think that maybe is an interesting.
The reason I chose 1 second as the resolution for this is because in Zurich the traffic signals, they are all on a 1 second clock. That was the reason, right?
Yeah.
So
Thanks.
But I'll take a look at this as well.
So I have 2 questions.
Yes.
First, for the simulation.
Yes.
If I understand correctly, you also include cyclists.
Let's take a look. Oh, I did in this video, yes.
Yeah,
But
I was wondering because I know in practice a lot of, at least for daytime traffic signals.
You can try and come forward to the video. Yes, please.
Yeah, so in a lot of daytime traffic signals, you do also have separate signal schedules for cyclists and pedestrians.
Yeah.
And there's also, I think depending on the intersection, we have also like the different like red buttons. So like how hard is it to scale your model to also count?
Okay, so the first thing I'll say is that this is in Switzerland, it's in Zurich, and it's not in the Netherlands. So there are little cycle lanes and stuff.
Yeah.
The detectors in this intersection, they don't even go on the cycle. Okay, so you're kind of a little ghost. But you know, there are some. It's not true that they are never taken into consideration. So while doing this work, we also looked at intersections outside of the city in the canton, and there they have separate cycle paths. They have loops in the cycle lanes essentially, and they also have buttons. But the thing is, you can just treat the button like a detector, right? You could have it, instead of it being number of seconds since the induction you detect the vehicle, be the number of seconds since someone pressed the button. So it kind of fits into that infrastructure of the detector. But I also did not have the time to look at those more rural intersections, and they're also much more dynamic. So it's a whole other challenge.
The other question I have is I also know with traffic signals, they do oftentimes switch between daytime patterns and nighttime patterns. So that's something.
So this is actually the case in this intersection. It turns off quite consistently between 1 a.m. and 5 a.m. Putting that into the decision tree is actually not so easy. I was surprised. I was like, oh, I will just put in the number of seconds since midnight. The problem with the decision tree is that when you have a variable which changes constantly, right, it means that there is no two samples during the day which are the same, because that second since midnight will always be different. That actually adds a lot of noise, which messed up a bunch of stuff. So essentially, the way you would simulate this, if you wanted to take that into account, is you would just pre-filter. You'd look at this traffic light, it has a separate state when it's deactivated in the data, and you would just figure out the time where that happens, and you just essentially create a separate thing that gets deactivated during this time. The schedule is fixed when it's deactivated. But I did also try to put that directly in the decision tree, but it was just such a big loss of performance to essentially, to do something which is trivial, right? Which is to look, oh, well, even you can use a script, right? When does it deactivate, and then match that in your simulation. But yeah, that's a good point as well. Yeah. Anything else? All right, and I will say again, please do share with Carlo, for example, if you have any experience using SUMO and you run into things that you just feel are wasting your time, because we really want to make this tool to make it easier for research, for control people to get into doing traffic research. That's really our goal with it.
Okay, so if there is no other question, let's thank the speaker once again.